Okay, I'm going to cover spin locks used in TempleOS. This is what I'm using this program to do is measure how fast it can change from one task to another. Yield, if we look up yield, what yield does is save the current context and then enter the scheduler to find the next task and then restore the context. So this saves a context and restores a context. Now, my operating system does not mess with page tables. I identity map, so I never need to mess with page tables. When I do a task save and a task restore, what I'm doing is putting the registers into a structure, and I save the floating point, and I remove breakpoints. And that's all that a save context involves. When I restore a context, somewhere in here I think I might have a lock. No, I guess not. Anyway, I got rid of those locks. So restoring is just the opposite. So if you think about it, if I have a 3 gigahertz machine, this is I don't know, 100 instructions. I don't know what it is. Anyway, it's not a lot. If 3 gigahertz, to make a long story short, I save the current task and schedule the next task as fast as possible with this loop right here. What it does is it sets a flag for this application being not done. Then it actually, we can put this properly. This should go down here. So what we do is we spawn a task on each. This is the core. So there are 6 cores, MP count. This is the core. And if we look at the spawn, it's the address of the task, a data item, name, and then the core. The core that you want to spawn the task on. So what we're doing is putting one task on each core. And what that task does is wait for this flag to be done and then yield. It yields over and over and over as fast as possible. And then once we get ready to end the task, then this waits for all the this sets if we have 6 cores, this is 63, 64 minus 1 is 63, and then all the cores turn off their bit, and then when all the bits are off, we're done. So let's go ahead and execute that. Let's Control B. So you saw this is actually an example of, anyway, so if you look at this, we're doing if you look at this, we're doing 4 million task swaps per core. So if you think about this, on other operating systems where you have to save the address map and restore a new address map and flush caches and stuff like that, flush, translate, look, side buffer, I don't know. Anyway, on other processors, on other operating systems, it takes much longer than, this is a quarter of a microsecond, 4 million a second. I can do 4 million a second. What that means is I have a new programming style that only I can do. Other people they can do 4,000, not 4 million. So it's wasteful. Anyway, mine is for home usage, like playing video games. So if you look at the number of tasks, actually the scheduler goes around on each core. We should only look at how many tasks on core 0. So right now we have the window manager, this task rep, the autocomplete is a task, that's this window, and then the atom task. So what happens is, let's suppose we yield when we wait for disk I/O. Okay, what I'm going to show you is my disk I/O. So we're going to go to, what we do is we read a port and then we yield. Then we read a port and we yield. So we're waiting for a disk I/O to complete. So when we yield, it goes from one task to the next task to the next task. Now, usually these other tasks are not ready, so it doesn't even swap them in. So what happens is it goes in the circle, and then it comes back to the top of the circle, and it swaps us back in, and we check it. Or this one is the current task. This one. So what happens is it goes in a circle, and it can do that 4 million times a second, go in a circle, if there's only one task running. So that's a new, you know, the funny part, you know what's hilarious? I find this really funny. An InInstruction takes longer than changing tasks. Do you want to see that? Let's go ahead and just for fun do import in U8 0x21 is a safe port to read. That's the interrupt mask. So this is going to lock it up. Let's do a yield. And so if we do this, so here we go. Let's see how much this slows it down. We can only do, so the InInstruction is we're doing one InInstruction and one task swap. So what is that? Half or 2 microseconds compared to okay, so the ISA is the old-fashioned in the early days. These were I guess 2 microsecond 500 500 hertz, 500,000 hertz. What I mean is 500 kilohertz. Anyway, so the funny part is reading a port takes longer than changing tasks. I think that's hilarious. Anyway, so let's analyze the spin locks we're doing here. So we're yielding. Okay, so now what's the performance? Somebody might think if we didn't yield, it would use up the whole CPU. This uses up the whole CPU, but it has no effect on performance. In other words, if we have 2 tasks, and let's analyze this. Okay, I've never done this before. U0 count I64 and I64I for I equals 1 I less than or equal n I plus. I'm just going to count out loud. Echoing to the, okay, so I say count to 1,000,000. Okay. So that took 1.9 seconds. 1.9 seconds, count to 1,000,000. Okay, I've never done this before, so I could embarrass myself. I don't think so. 1.9 seconds, 1.8 seconds. Okay, so let's see what happens when we run this task at the same time. Okay, so we kick this on, and if we look over here, we're doing 4 million, and then if we come over here, this is 1.8. Let's see what happens. I'm excited. Count 100. Oh. What do you think it's going to be? From 1.9 to 2. Okay, so that's pretty impressive, isn't it? We're using up an awful lot of, that's with all cores pegged, using memory bus cycles and stuff. So now what happens if we run that same task multiple? Well, anyway, okay, so let's analyze our spin locks. So in the disk code, when I lock a device, if I'm the owner, I don't have to relock it. Otherwise, we do a locked. Okay, we're using two different terms, lock and lock. This is this lock bit test and set is an assembly instruction that uses a bus lock. You use bus locks if you're doing multi-core. Otherwise, you can just use the atomic bit test and set. Anyway, so we're yielding. So this is doing that thing that takes a quarter of a microsecond. So let's analyze this. This lock forwarding, I used to allow a partition within a partition. I think what this is anyway. I'll have to check to see if that's still being used. Anyway, so if you do a CLI and then not okay. Let's go back to. Sorry for not. So there's a pause instruction. When doing CLI, what that does is that locks out. That means one task on this core. That means we're the only task on this core that is accessing this code. We are the only task on this core that is accessing this code. We will this makes us the only task. This is for multi-core. We lock it with a pause. The reason we don't do yield is this is the locking, excluding other tasks is completely free if we do push CLI. We start spending a little bit if we have other cores accessing. The normal situation is I never have locks being fought over. I have like 5 tasks, and none of them really, I never find an application where I'm fighting over a lock. Now, if multiple cores were trying to fight over this, then this might be a problem, kind of wasteful. But since the normal is for it to immediately have access, here's an example. The Atom task has a heap. It's kind of like kernel memory, and all tasks might find a situation where they want some Atom memory. And so what I would do is I would do a CLI, and that would lock out other in the heap code. As a matter of fact, all the heaps have, the partitions have locks, the heaps have locks, and pretty much everything you can imagine has locks. So on malloc, what we do is each heap has a lock, each block pool has a lock. Here we are. The CLI immediately gives us, most everything is on core 0, to be quite honest. So this CLI is completely free. Nobody's going to malloc until we come back. Malloc is ours for the taking. No one's going to mess with malloc or free. Free is also CLI locked. So malloc is ours. We own it. And what this does is it locks it if there's other cores. So this is an expensive spin, but we never have other cores fighting for Atom's heap. If multiple cores were fighting for Atom's heap, this approach would be bad. You wouldn't want to do a server with this, but if you're just doing video games, you're not going to have a problem. My vision is a Commodore 64, not a mainframe. So, where in a video game are you gonna? Maybe you use multiple cores. Anyway, so that's the story. Pause is a I don't know what it is exactly, but in a spin loop you use pause. Anyway, it's that voodoo stuff of CPU timing. So you lock the bus for, or you lock, I don't know what this does a lock you have to do for multi-core stuff. And it has to be 1 per cache line, but I don't really check for that, but it's not, it would never happen 2 in a cache line. Anyway, so what other locks are there? So some of them have ownership, like I showed you the partition and block device. Block device is a lower level than a partition lock. A block device is a disk. A partition might be multiple partitions on a disk. Anyway, so I have partition locks and block device locks. I have heap locks, and then each heap draws from a block pool. There's a pool of memory that each heap draws from. So when the heap bites off a chunk, and then the heap bites off another chunk from the block pool, and those block pools have locks and heaps have locks, multi-core safe locks. Documents have locks. If you go to the docs, when it updates the screen, it locks the screen document. It turns out that when it's updating the screen, when it comes to your window, if the window manager tries 10 times, and if it's not able to get the lock, it gives up and you have a flicker. So on this. waiting for the bird. So the Jiffy frequency is one kilohertz. So we take 1,000 divided by. So I don't know where I came. I just invented that number. So it checks if it times out, and it tries to get a lock. And if it times out, if it doesn't get the lock, then it just has a flicker cycle for that window. So documents have locks. When the document is a big deal, you will find yourself using the document structure. Anyway, so how about that?